I will talk about pruning the tree. Of course, you can do the babysitting way. So let me do a second tree. And I'll rename this tree as the maximal tree. And the second tree would be best classification tree. And to start out, I'll also do interactive just to show how to do the pruning. Let me train the tree automatically. Go back. So far, when growing the tree, it uses the log worth metric. So now let's take a look at the pruning process. Think about the objective of training a machine learning. We want to predict the donation behavior, right? We want our model to be able to predict donation with least amount of error. When I say error, it's a misclassification. For now, let's say correct classification is good. Incorrect classification is bad. False positive and false negative are equally bad. For now, let's assume that. So in that scenario, we would choose the model that has the lowest misclassification error, which means it has the highest accuracy. But so far, we haven't done that yet. When we grow the tree, we didn't take into account the model's misclassification error. We simply look at all the possible splitting alternatives calculated by using the chi-square test. And we grow the tree over and over and make the tree more complex. So that's a metric that you will use to select the best tree. Now, if you imagine the maximal tree, if you cut anything away from that tree, it becomes a different tree. It will lead to somewhat different performance. If you change a lot, you prune this part, you decide to continue to grow the other part, it becomes a different tree, and the overall performance may change. So with the maximal tree, you have opportunity to reshape it into subtrees. What you want is do a systematic search. A systematic search will exhaust every possibility in pruning the tree, one level at a time. And then you compare the thousands models in the end and see which one performs the best using the test data set. Let me show you the result of that. So I only grown a tree that's so far. And the SAS ran to grow the maximal tree and calculate the node statistics. It hasn't pruned yet. So what I'm going to do next, we'll let SAS do the pruning step, and we'll see how fast that goes. And I will select a metric here by. So let's see. Use priors? No, we're treating false positive and false negative the same. We're not assigning different weights. Exhaustive 5,000. So 5,000 different is the maximum number of searches or alternative trees that the SAS will search. 5,000 would be sufficient for this case. And then subtree is where SAS optimize and choose the best tree. But how does it choose? Which metric does it compare the different trees? Default is decision because the target variable is nominal. It chooses a decision by default. But here, decision would be no different from misclassification because we assign equal weight to different outcomes. So it will be the same result either way if you leave it as default or you choose misclassification. So I've chosen that. That's only a change of property. It didn't lead to any calculation. But when I run it, and notice this time I didn't freeze the tree. I let the SAS do the pruning search, and I have customized the criteria. Now I let it run. This is triggering the pruning process and the search and optimization. So I will show you the result, and then I will explain to you what SAS has gone through. So it only takes maybe 5 seconds, right? There's a graph that's important. The graph is the overfitting graph that doesn't automatically show, so you will have to call it. It's called subtree assessment plot. And make sure every time you look at the assessment plot, you need to make sure that the metric is the one that you designated. It doesn't automatically choose it, which is stupid, but I guess SAS assume you're intelligent, so it doesn't it doesn't do things for you too much. So I chose the misclassification rate. All right. So what does it do? The number of leaves indicates the complexity, right? Whenever you see the overfitting graph, the x-axis is always the complexity, but it's different parameter for different models. For regression, it's number of coefficients. For trees, it's the number of leaf nodes, right? So another way to represent complexity. The maximal tree may have close to 57 leaf nodes, right? So that would be the maximal tree at this point that the graph can go. It can go anyway, any more complex, and the models on the left are more are simpler, right? So this would be conforming to what you expect from overfitting graph, right? The y-axis is the error. As it started out, the accuracy is 50-50, which is the worst. Yeah, it doesn't help at all. And as you grow the tree by 1 or 2 or 3 splits, it quickly goes down to 40%. And then as it grows more, it increases more. You notice that the blue line continues to fall because that's the training performance. That's a training set error rate. It eventually becomes very small. It doesn't go to 0. Interestingly, for trees, it doesn't work like that. It won't account for every error in the training set, but still it goes down to significantly low. But at some point, the validation set performance will reverse and go, become increasingly bad. That's the point where the optimal tree is chosen here, right? And a line is indicated where the final optimal tree is chosen by the model automatically, and you can hover over to see how many leaves are in the final tree. I noticed that when you scroll across these number of leaves, the vertical line indicates that that's the same model, but performance is different on the 2 partitions. That makes sense, right? So this vertical line is indicating the same model. Its performance on training is close to 41%, but performance on validation set is close to 43%, the error rate. If you change it to a different metric, it still shows you the result, but it's not selecting the optimal model according to this metric, because the model wasn't selected by using this metric in the first place. That makes sense? If I had selected average square error, then this model would have been selected. Great. Okay, so SAS, it's good. SAS compared the subtrees at every level of complexity and graphed the performance for you under both partitions and have chosen the best tree according to a metric. That's good. That doesn't sound very intensive. It's only 60 trees. It doesn't sound a lot of calculations, right? Let me show you what's happening in the back. It's much more than that. So what happens when it split and when it prune? Using 2 variables as a demonstration, the data will look like this. The color of the points will indicate the target variable. There are 2 colors. x1 and x2 are two input variables. So if you do splits here, it's basically cutting areas on this plane by using rectangles. So let's say the tree has been grown, and the first split is using x2, using a level of 0.6 somewhere close to here. Then it will draw a horizontal line. Everything above it, it will be split into the right branch. Everything below that will be split to the left branch. And then it uses x1. x1 is making vertical lines, further cutting the plane. But the two split level on the upper plane and lower plane can be different because it's under two branches. It can be completely different. If we focus on this point, the point has x2 as 0.7 and x1 as 0.3. By the first split, it will be included in this branch. By the second split, it will be included into this branch. So it will be something like that. And then based on the points in that region is like that. 70% of the points has green, right? So the confidence for green is 70%. The prediction will be green for this point, even if this point is actually white. Prediction has to be applied to all the points in this split. So if you can imagine, decision trees are basically cutting board in the higher dimensional space all over. And it can zoom into a very particular cube and has a prediction that's the same as some other cube. In this way, the model is not linear, right? The influence that one variable has, this variable x1, has influences at different points by different levels. Sometimes that variable is used to split based on one level to make predictions separately. At another branch, another level of that variable is used to split the sample and make other predictions. So the relationship between a variable, its values, and the outcome is not linear. It can be very different according to the specific sections. After you have a maximal tree, you have a big tree. After going through different ways of cutting, then you need to prune it. Then the pruning process. You take the maximal tree. Let's say now you have grown a tree that has 6 leaf nodes. So in this case, it starts from that and calculate the performance of that tree in training and validation set, record the results, and then start pruning. By pruning, it removes one leaf node. So every prune removes the total number of leaf nodes by 1. There are two alternatives to prune by 1. You can't think of any other scenario where you can prune by 1 with this maximal tree. SAS will prune and then calculate the performance of these two trees with regard to the training and validation. So you have a result. Suppose the left tree is better. SAS will remove the worst ones and only retain the best one and record the performance and draw the graph, right? So that's a tree with 5 leaves. Then it moves on to 4 leaf nodes. You have 3 possibilities. Each time it will start from the maximal tree. It will exhaust all the passes. So in this case, there are only 3 possibilities by going from the maximal tree. And then again, SAS will calculate the performance and retain the best one and move on to the next pruning job. So the more you go up, the number of possibilities there are, and SAS will always exhaust all the possibilities for you. So that's a lot of calculation. Then SAS will draw the graph. Every model at a point is the best model of that class. Then you see 2 lines, and then you will pick the simplest model that has the best validation set performance. So that's how SAS picked the optimal model. Think about the criteria that SAS select the best model. In this case, SAS doesn't use log p. It doesn't use the chi-square test. It uses the ultimate criteria that we care for. It's a misclassification rate. So you can almost think of the growing and the pruning process are 2 reverse processes, but they use slightly different metric. The pruning process is closer to the ultimate objective. The growing process uses some statistical tools to grow it. You can't use both at both paths because you quickly exhaust your possibilities. This way gives you more possibilities of exploring possible trees. So the misclassification rate is simply the percentage of misclassifications. you have a big summation of every misclassifications. When the prediction is different from the outcome on the validation set, then it's a error. It's a misclassification. So all the misclassified cases are calculated, divided by the entire sample. So that's the sample-wise misclassification rate. Another criteria is to compare the mean square error. In the binary target variable case, you can also use that, and it produces somewhat different result. As you see the overfitting lines, it produced differently optimal model, because this model will optimize average of the squared error. It takes into account the confidence, the precision level of each leaf node, not simply a misclassification. Right? Some of the leaf node has 90% confidence, and that will contribute to the reduction of mean squared error. Some of the other leaf nodes have confidence level of 55%. That's quite vague. So that will add to the mean square error of the model. So using this measure will produce somewhat different tree than the misclassification rate. But it's harder to explain what happens here. What does it really mean? You cannot use plain language to explain it. It simply is a mean square error. But for someone who doesn't understand equation, what does that really mean? How much error is it? As versus the misclassification rate. It's very simple to explain. It's simply the percentage of mistakes that make across all the sample. So that's easier to explain. So I have two trees. Let's use a tool that SAS provide for you to quickly compare the performance of all the different models that you have done. This is something that you will do later in the homeworks and in the project. After you have trained all the models, how do you select them? Within each model, SAS do provide the tool to select the best model, right? But that is under that particular setting. With the best classification tree, the metric I use is a misclassification rate. I could train a different tree, and I select the mean square error as a metric. So that becomes another tree. I'm not sure ultimately what is the best tree in making decisions. So I can use that tool to compare the different models, and I can also have neural networks. Then I use that model comparison tool to compare neural networks and trees and regressions and different models. So after you have multiple models, then you can go to assess and use model comparison. Then you can connect all the models that you want to compare to the model comparison node. It's very critical at this point to specify the metric that you want to select the ultimate best model. It can be different from the one that you chose for a particular model, right? It can be different. And sometimes you deliberately want to do that because you want to maximize the search process, right? That's the same mentality as if under each tree, decision tree node will try to search all the possibilities and compare them and select the best one. Here, you want to generate as diverse a set of models as possible, even going with some of the specifications that may not make sense immediately, right? What I mean is that if you have a best classification tree, and if your model comparison wants to select the best misclassification model, you would assume that this one performs the best. But that may not be true because the pruning process is very complex. The training process is also very complex. So sometimes you maybe want to deliberately train another tree that selects the best mean square error and compare with this one and let the model comparison node find out which one is the best, right? So same mentality. You want to sometimes be crazy and go outside your comfort zone to train more models, just for the purpose of searching for possibilities, right? So here, I will select the misclassification rate, and this comparison of the different models also uses the validation data set, right? But you need to specify. Otherwise, this is another stupid side about SAS. It should simply, by default, use validation set. But the default is train. So if you leave that as unchanged, then that would be definite mistake to do, right? So make sure you change it. Model selection, change the selection table to be validate. Or sometimes you can use test, but definitely not train. If you've done that, if you leave the train there and submit your work, I would assume it didn't learn at all, right? That would be a serious mistake to do. So always check if you have specified the correct set. After that's almost the only thing that you need to change. After that, you will run it. For model comparison purposes, this table shows you which one is a better model. It will rank them based on the metric that you selected. The metric that you selected is the validation set misclassification rate. So I was comparing a best misclassification rate, best misclassification tree with the maximal tree. The misclassification tree had slightly lower error on validation set, though that's why it's chosen. If you look at the train misclassification, it also has a lower error for some reason, just because it's less complex, right? So it has lower error on both partitions. If you look at the validation set mean square error, validation average square error, it's very close. It's not different by a large margin, but the misclassification tree still does a little bit better than the maximal tree. So it's a very clear comparison. There are other reports about the results, like ROC chart, lift chart, cumulative lift chart, and gain chart. We'll talk about these in maybe chapter 10. After we talk about regression. After we talk about neural networks, we'll talk about different tools that you can use to compare models and think about decision rules. Then we will use these charts. Any other questions about decision trees?
So in this case, maximal tree is better, right? If you say that the mean square error is low in that case.
In that case, yes. Yes, in this case, yes. Yeah, very odd, huh? Even the maximal tree is. Yeah, you would think that the best classification tree would be better. But yeah, so sometimes. So that's why I suggest you sometimes train models crazy models, and sometimes you discover a model that works better.
Though the maximal tree is on the
it is on the validation set. See, it lists the results both for validation and training set. This one, selection criteria, is the validation set misqualification rate.
Initially you said that in the minimal tree node, in the case of growing tree, it does on training set, and in that other best classification, it does in the validation.
Did I say that? Well, let me clarify. When it splits, it always uses train. Yeah, when it prune, it always uses the validation set.
But pruning is used in best classification, right?
Yeah, both cases. Yeah. It's
Or in the maximum.
Yeah, so
Not used.
it's not intuitive, but maximal tree does give you a more complex model. And it does seem to be worse, right? Here, this shows that there is a subtree that performs better than the maximal tree. So there should be another model that outperforms the maximal tree, right? But the result shows maximal tree is the best. Yeah. I would suspect did I specify the right assessment? Disqualification. I think to answer that question thoroughly, I need to look into it. It is a surprise, at least from the result, right? Maximal tree is expected to be worse than best classification tree, but somehow here it's better than the best classification tree. Yeah, I think I need to look into it. Any others?
From my result right here, the best algorithm is for the best classification tree.
So your result is different.
Yeah, it's different than.
What's your error? What's your error rate?
You mean the mean square error?
What did you select the mean square error?
No. What did you add?
Do you have the same column name as here?
Yeah, and the best classification tree is 0.423633.
Okay, so yours is better than this result.
Yeah.
Right.
And the bottom one is 0.424407.
So that's the same. So somehow you have a better result here for the best classification tree. Maybe because some of these settings could be, yeah. Maybe we can talk more after the class. Let me find out if we have the same settings or what different do we have that, produce a different model. Other than this, what other questions do you have? Good?
I have one related to the homework.
Right.
And the homework, it says create a full set of the rules, like generate a table.
Mm-hmm.
Do you do that within the interactive decision tree, or do you make a new node to generate a table?
Well, that is the one I was talking about a lot of information, and it was analyzing different nodes and the if-else condition, and then the confidence and the cases. That's where you will get the information. It doesn't matter if you use the interactive or if you don't use the interactive. Do you know where to get that information? After you have trained the tree.
With like, I can only do it per node. It wants a full set, but I can only get it per node. So I don't know if I'm supposed to.
Well, that's
do the
not.
table.
Well, you can get the full set.
Oh.
You should be able to get the full set. After this class, you may want to review the video, the first half. Any other questions?